Picture this scenario. We've got a button on the moon's surface and we're itching to find out what happens when it gets pushed. The thing is, we're down here on Earth and the button's all the way up on the moon, but no worries, we built an iron bar that goes from the Earth's surface all the way up, almost touching the button. All that's left to hit the button on the moon is for you to give it a nudge. The question is how long until the button gets pushed. To make things a bit easier, I'm going to give you 3 options. Option A, the button's going to be pressed as soon as I give the bar a nudge. Option B, the button's gonna get pressed, but it'll take a while. And for option C, the button won't be pressed. To start answering that question, we gotta understand a bit more about what exactly is going down. We're here on Earth's surface and got a button on the moon. And just to keep things simple, we're gonna pretend like neither the Earth nor the moon are moving. Since the distance between us and the button is about 385,000 kilometers, we've rigged up a bar that lets us reach the button. What this thought experiment is really asking is, will the info that I move the lever get to the moon instantaneously? If your answer was choice A, then you're thinking just like Isaac Newton used to think. Back in Newton's day, folks didn't have a clue about the true nature of light or information. In fact, for Newton's law of universal gravitation to work, he had to say gravity moved instantaneously across all space, meaning at infinite speed. If this condition wasn't met, the planets would always be pulled towards where the sun was located in the past. Then the orbits we know wouldn't work. It's not just gravity where the idea of instant action exists. From the viewpoint of classical physics, a bar is traditionally considered to be a rigid body, and a rigid body is essentially just an object that is made up of more than one piece, where the pieces are tightly connected and the whole bunch moves as a single unified object. So, if a bar extending to the moon is seen as solid, when I move it in my hand, the moon's end moves at that instant, instantly. The idea of instant action was part of the whole Newtonian physics package. It wasn't the main focus of the theory, but it had to be there for the whole thing to work. So, Newton wouldn't have been astonished that the idea of a rigid body is kind of fuzzy. But first, we gotta understand why the idea of instant gravity is also off base. For a good while in human history, this idea that gravity had infinite speed didn't seem off base, until a French astronomer named Urbain Le Verrier discovered something strange with the planet Mercury. According to Newtonian mechanics, every orbit is an ellipse with the system's center of mass occupying one of the focuses. If you draw a straight line between the 2 farthest ends of the ellipse, you've got what's called the major axis. If we just had 2 bodies, one orbiting the other, all this would be fixed in space. But real life, as always, is more complicated. And the other planets and bodies in the solar system exist and mess with each other. This creates a movement in the major axis, which spins around the center of mass of the system, and this movement is called the precession of the orbit. Le Verrier found out that the precession of Mercury's orbit, even when all sources of disturbances were accounted for, was way more than expected. It looked like there was a hole in Newton's theory of gravitation, and it wasn't patched up until Einstein's general relativity came along in 1915. Einstein figured out that gravity wasn't just a force anymore, let alone one that spreads at infinite speed. The general theory of relativity started to see gravity as a result of the warping of space-time, and as a bonus, it clued us in on the fact that what we experience as the force of gravity moves at a speed limit, which is the speed of light. And that's exactly why there's this famous saying that goes, if the sun were to vanish right this second, it'd take us about 8 minutes to even notice. The gravitational attraction that all of us, including planet Earth, indeed feel, which keeps us in orbit around the sun, travels through space at the fastest speed anything can go, which is the speed of light. And the same thing goes for the light from our star, which moves, as the name suggests, at the speed of light. If the sun vanished now, we wouldn't know until 8 minutes later when it all went dark and society went into disarray. And why am I beating around the bush, talking about physics history to solve a simple thought experiment? Because it's cool. And also because I need you all to grasp one of the most important concepts in your lives. Nothing's instant in the universe. No matter what we're talking about, it's invariably always going to take a while for the info to spread. When you gaze at the night sky, you're actually seeing into the past because the light from those stars took years to reach your eyes. When you're at the table talking with someone, the sound coming out of their mouth was actually made a few milliseconds before it hit your ears. Alright, in this case you can't even distinguish the difference, but the point is you're basically living in the past. Your brain just got real good at adapting to that. Or, if you want a more dramatic case involving the delay of sound waves, next time you're at a stadium or a concert, pay attention to how the sound behaves when folks are clapping. The farthest applause will reach you with a delay, and as a result, it looks like half the audience is clapping out of sync. When in reality, it's just an auditory illusion because sound takes longer to reach your ear. The speed of light only seems infinite to us here on Earth because it's way too fast for us to notice its speed in our daily lives. In a second, a beam of light could lap the Earth 7.5 times. But as soon as we started dealing with longer distances, that speed, which isn't infinite, started to become more noticeable. During the Apollo missions, which sent humans to the moon, the communication between Earth and the astronauts has a pretty clear delay of about 2.5 seconds. That's because the signal sent from Earth takes about 1.25 seconds to reach the moon, and the astronauts' reply takes 1.25 seconds to get back to Earth. So, now that I've beaten around the bush, and I hope you all got why this experiment is actually about the speed of information, it's time to give the right answer. And the answer is option B. Immediately when I push this iron bar here on Earth, it's going to take some time for the info that I pushed the bar to actually travel all the way to the moon and hit the button. Now the question is how long this is going to take, and lucky for us, figuring that out isn't too hard either. We just need to figure out how the info that I pushed the bar is spreading, and there are two important speeds of propagation in this experiment. I'm going to start with the speed of light to get that out of the way right off the bat. As soon as I push the bar here on Earth, the visual info that is transmitted through light is going to start its journey to the moon, which will take about 1.25 seconds. If someone was on the moon on the side equipped with a powerful telescope, they could see me 1.25 seconds later actively pushing the bar. But this is where we get to the meat of the answer. The bar won't budge. Even after I push the bar and the info in the form of light that I push the bar reaches the moon, it still stays almost touching the button. Actually, we're still a few hours away from hitting the button. The most important thing here is what the bar is made of. In this case, iron. The information that I move the bar will spread at sound speed in iron, roughly 5,120 meters per second. For comparison, sound in the air travels at just 343 meters per second. So, when I push the bar, the info that it needs to move towards the moon will spread like a mechanical compression wave all through the bar, nudging each part a tad closer to the moon. All in all, it'd take about 20 hours, 53 minutes, and 15 seconds for the info to reach the moon. It's simpler to send a radio signal at light speed asking someone to press the button, right? And the way to see this more distinctly is to completely ditch the idea of a perfectly rigid body where all parts move at the exact same time. We can think of the bar as a bunch of iron layers stacked up, and what I did here on Earth was to push the first layer, which then pushes the second layer, which then pushes the third, and slowly passes the push all the way through the bar. So each piece of the bar has its own independent movement when we ditch the rigid body approach, and the pieces communicate with each other at the speed of sound in the bar. If you're doubting me, there's a similar experiment you can try out at home, and all you're gonna need is one of those wacky slinkies we used to play with as kids. The idea is to hold it like this so that the bottom part hangs loose. Now grab your phone, set it to record in slow motion, and watch what happens to the bottom part when I let go of the top part. As you all can see, the bottom part of the spring keeps hovering, even after I've actually let go of it. That's essentially happening because the news that I'm not holding the top anymore is still making its way down the spring. And the bottom part only begins to drop when the news that I've let go of the spring finally reaches it. It's almost like they forgot to inform the bottom part of the spring that it needs to strictly obey gravity. But honestly, truly, it's all good. It's still adhering to gravity. It just hasn't gotten the memo what forces are acting on it. I find it fascinating how we can uncover a whole deep sea of new concepts in such a simple thought experiment. I hope this video also taught you all something new. According to historical records, Einstein was really into thought experiments. And one of the reasons was that they helped to think deeply outside the box. If you got any questions, just drop them in the comments, and then we can all learn together. Thanks a bunch, and see you next time.